Hi folks, in this lecture I'm going to quickly go through the material we'll need to work on problems from section 1.4. That's entitled Function Notation. And let's see, the first thing in function notation, I might as well just show you what I mean by that phrase. This is what it's called when you write something like y equals f of x. So this is being abstract, right? I don't know what f is, but f is supposed to be the name of the function, and x is the input variable. So the notation here, unfortunately, it looks just like, well, it looks like you're just doing multiplication, and you've got some extraneous parentheses, but that's not what it means at all. That's the function's name, and x is the input variable. And then in this case, I've assigned the output to a variable name as well. That's entirely abstract. If I want to say something about a particular function, I'll actually often write, well, let me give you an example. Suppose you write f of x is equal to about x to the second power plus 1. Here I haven't named what the output variable is. I've just written down some math that tells you what actually this function f does. That's the idea. So we're now, what's really happening with this equal sign is we're defining what the function f is all about. It's, if I say it in words, f is the action. By the way, functions should be thought of as verbs. They're doing something. Here, f is the action that first squares its input and then adds 1 to the result of that. There's a fairly easy process of what's called evaluating a function at a point. Like, for instance, when x is 1, I would write f of 1, and I would say, well, just plug in a 1 where the x's are. So you get 1 squared plus 1, that's 2. If I wanted f at 2, that would be 2 squared plus 1, which is what, 5. So this is sort of abstractly defining the function. This is evaluating the function at particular x values. There's actually a different thing that you can do, which is ask what x value in a function gives you a particular y value. So, well, that looks like this. Suppose you have f of x is equal to, let me do a quick one here, 10, say. Okay, in that case, we have to do what's known as solving for x. And usually it means going back to the way the function was defined and doing a little bit of algebra. Sort of, in a certain sense, a lot of the hard work in algebra is about solving that kind of thing, where you don't know what the input value is. They've specified an output value, and your job is to kind of reverse things and figure out what the input value is. I guess while we're looking at that particular one, I should go ahead and do it. My function f was squaring and then add 1. And I'm looking for when does f of x equal 10. So it's saying x squared plus 1 equals 10. That's just replacing the abstract way of talking about the function applied to this variable x with this piece of algebra that defines what the function is, and then setting that equal to 10, right? And can we solve this? Actually, it's not very hard, is it? You take a 1 off of each side, so you get x squared is 9, and then that says x is 3, doesn't it? No, not quite. You should have a plus or minus in there. Yeah, because -3 squared would also get you 9. So remember, when you're doing any algebra that involves square roots, you gotta keep track of that idea that there might be a minus sign in it. the negative square root also has to be kept track of. Anyway, that's not the focus of what we're doing right now. Mostly just want to talk about this kind of functional notation, the f of x thing, and then give you some terminology for some of the parts of such a thing. So first I should mention, I feel like the book misses something here, that the name of that notation is actually honors Leonhard Euler, who was a very famous Swiss mathematician. So it's actually known as Euler notation. And when we have that prototypical Euler notation where y is equal to f of x, I often call that x the input variable and y the output variable. There's other names for them too. And the names are, well, I think less clear than input and output, so I most often use those words. But we also have independent variable for x. It's independent. Can I put an AKA in front of this? AKA independent variable. The output variable is also known as the dependent variable. I don't know, maybe both of these sentences should be in parentheses. They're just parenthetical remarks. So the input variable, also called independent, you notice the match of the prefix in both of those. The output being called the dependent variable, that actually makes sense to me because you can think of it this way. The value of y depends on the value of x. I want to, in addition to this terminology, there's some places where these input and output variables respectively live. The stuff on the input side, this is called the domain. So I need to be a little careful about how I'm saying this to you. The domain is the set where the input variable can take its values. So it's not like these are equal, but this is like a place where these guys live. Output variables are associated with a set as well called the range. And there's another name, which unfortunately our book doesn't go into, but there's another name that goes with this left-hand side, or the output variables. It's called the codomain. So I want to try to explain range and codomain as well as domain, and there is no such thing as a co-object on that side. There ought to probably be something called a co-range on that side, but people have just defined their way out of that. So on the input side we have domain. On the output side there's actually two sets where the outputs can be. Actually the distinction there isn't that hard. If I were to put it in words, the codomain is the places where the outputs could be. The range is the set where the outputs actually are. Right? The actual values of y that appear when you let x range over all possibilities, those things make up the range. The codomain is just sort of where they might be as opposed to where they actually are. All right, so there's two other ways two ways to visualize this Euler notation function and its input and output variables. One is what's known as a black body diagram. Engineers use black body diagrams all the time. Sorry, I'm saying I was just looking at a physics problem about black body radiation, so I just used the wrong word. I was supposed to say black box diagram. And especially in electrical engineering, they use black box diagrams, and they look more or less like this. They're specified by what are the inputs and what are the outputs, but it's sort of like it's like a machine, you know, and the what happens inside the machine is covered up by the casing on it. So you could even sort of picture like a conveyor belt. X comes in on this side, something goes on under the hood there, and you don't know what it is, but what comes out is Y. So X is here, Y comes out, and the functions, this change, this metamorphosis, the process that happens to X and as it gets turned into Y. We don't have to know what goes on in there, but when we do know what goes on in there, that's the part where you say, okay, f of x is equal to some formula. You could specify what happens inside the black box by giving an algebraic expression for what f does to a generic x. That's basically peeking under the hood. So, well, I guess that's enough to talk about black box diagrams. They're a way to visualize this stuff. For us, we've got functions that are just the simplest possible thing. You got one input, goes into the black box, gets messed with somehow, and when it comes out, you get one output. There can be much more complicated things. I mean, real engineers, real electronics engineers might have 20 or 100 different inputs going into a black box and a similar number of outputs. But we're dealing with the simplest possible case where it's one in and one out. Another kind of visualization for functions is gotten from Venn diagrams. And here's where we'll see the codomain and range business. Venn diagrams are, well, they're fairly common. I bet you've seen these things before. We indicate a set by just drawing a loop or some sort of, often it's a circle, but it can be kind of egg-shaped. It can actually be kind of wonky if you need it to be. But a boundary needs to be drawn in any case. And then you put some things inside of the set by just drawing dots in here. Now, if you have particular elements in mind for what goes in the set, you might label them. Like I could have 1, 2, 3, and 4, and 5 in that set. But you can be more sort of generic. All the points in there might be elements that the function can act on. I need to have, this one here is going to be possible values for x, right? And I'll have a second loop over here with possible values for y. In fact, why don't I go ahead and give you some y values over here. 2, 5, 10, 17, and 26. And I'll show you which things go to which. Now I'm going to draw f. I draw f by drawing an arrow from the input to the output. 1 goes to 2, 2 goes to 5, 3 is going to 10, 4 to 17, and 5 to 26. You're basically, in this case, you're describing f by showing all of these arrows. So on this picture, we're hiding the details. On this picture, I'm showing every detail, showing the exact route that 1 gets sent to 2. By the way, some people call these sniper diagrams, which is a little gross, but you could think of the things on the left-hand set being snipers that are aiming at people over there. So these arrows literally would be bullets traveling, or maybe arrows, depending on what century your sniping was going on in. There's a little bit of funny business that I should mention with the arrows on these kinds of diagrams. First of all, an arrow that connects 1 to 2, that could be identified with a pair that has 1 in the x position and 2 in the y position. In fact, those are inputs and these are outputs, so x and y make sense. A pair that sends 2 to 5, well, that would look like 2, 5. Again, x and y. 3 to 10. 4 to 17. That looks like 4, 17. And finally, 5, 26. Now, if I put these ordered pairs that I've just created, or just really copied from the arrows, into a set, that is, put them in curly braces, what I've just done is written a set of ordered pairs. That's a relation. Any set of ordered pairs is a relation. And so what I'm emphasizing here is, again, the idea that a function is just a particular kind of relation. What's the problem that a function, or that a relation might have, which makes it not be a function? If you have the same input go into two different outputs, then it's no good. It won't be a function. So I want to recognize that functionality. When is this set of ordered pairs, or equivalently this sniper diagram, telling us we got a function, and when would it not be? Now that particular function is the one I was playing with a second ago. It was x squared plus 1. But I could be completely abstract about it and give you a different function just by drawing a Venn diagram, maybe with 1, 2, and 3 in it. And here's the other side. That'll be letters, A, B, and C. Perfectly fine to have a function that takes numbers to letters. It's just some collection of arrows. How about if 1 goes to A, 2 goes to A, and 3 goes to A? It might be a stupid function, right? I mean, it's kind of silly. It's just everything goes to A, so it's not very hard to describe. As a set of ordered pairs, it would be, well, what would it be? 1A, 2A, and 3A. Is that okay? Is that a function, or does that fail to be a function because of this, well, essentially what's the vertical line test? Yeah, this is actually okay. You can have a sniper diagram like this, where each element in the domain goes to just one element in the range. Okay, I'm using the words now. I better say what they are. This thing, the set of possible outputs, that's your codomain. This thing over here, the set of inputs, that's your domain. If it's going to be a function, every single thing in the domain has got to have an arrow leaving it, and this is fine, it does that. It's not the case that everything on the codomain has to have an arrow landing on it, and the things that do have an arrow landing on them, it's in this case it's just the letter A there, that's a set, and that's the range. Range is outputs. Potential outputs are codomain, actual outputs are range. The domain contains all the inputs. There's no such thing as elements on this side that don't go somewhere. Okay, so that picture is just fine. What you can't do, if you're planning to have a function, let me just recreate the whole setup again, but I'll use different arrows so I'll make a different relation. 1, 2, and 3. A, B, and C. What I can't have is this, that 1 goes to A and 1 also goes to B, and maybe 2 and 3 both go to C. This part is fine. It's okay. This part where it diverges, I'm just going to make an unhappy face here. That's sadness. It's like you've got a bow and arrow and you're trying to shoot one guy, but you're going to try to string up 2 arrows in it, like Legolas, and you're going to shoot, and the arrows are going to go in different directions and hit targets. Yeah, that's just not going to happen. So asking a single input to go to 2 different places, bad. Having 2 different inputs that go to the same place maybe seems like a waste of effort, but it's perfectly fine to do that. So this divergence, this thing where 2 arrows split off of the same input, that tells you not a function. Maybe I'll put a thought bubble on there and I'll say not a function. Even though this is not a function, it's still a relation, and we still have a domain, and we still have a codomain, and we even have a range. In this case, the range and the codomain are the same. Everything in the codomain has an arrowhead landing on it. Oh, well, there's a problem that often happens when you have a notation that's new and it looks kind of like something old. And that's one of the problems with Euler notation, is it just looks like multiplication. You have to know somehow from the context that you're dealing with a function being applied to an input variable and not multiplication. But if this was multiplication, if I said f of a plus b really meant f times a plus b, then you could distribute that multiplication. And you would get f times a plus f times b. But if this is not multiplication, if it's function application, these two things generally are not the same. I mean, I guess it can be. Occasionally you'll get coincidences, but the general rule here, nah, you won't have that. As an example, how about if I took the function we've just been playing with a couple of times now, f of x is x squared plus 1. Pretty simple function. And I'm going to have a and b be 1 and 2, respectively. So what's f of 1? That was 2. And what's f of 2? That was 2 squared plus 1, that's 5. F of 1 plus 2, which is the same thing as saying f of 3, yeah? What's our function again? Square and then add 1, so squaring it gets you 9, and then add 1, that's 10. But f of 1 plus f of 2 isn't equal to 10. In fact, it's equal to 7. That's what's known as a counterexample, by the way. I'm sort of proposing that it might be the case that f of a plus b is f of a plus f of b, but then I'm showing you it doesn't always work. So if it doesn't always work, we usually don't care about it. We only state rules of algebra if they're always true. If they're only going to work occasionally, then that's just not good enough to be usable as a valid form of reasoning. Okay, so yeah, this is something to keep in mind. F of a plus b is not going to be the same as f of a plus f of b. I'll give you an even simpler example of this that people get fooled by all the time. It's such a common error. It's known as the freshman error when you take in calculus. If the function is squaring, if you have a plus b and the function is squaring, it looks like that, right? A plus b squared, if you sort of separated it out this way, you would say it would be a squared plus b squared, right? And that just looks so reasonable that people go, sure, yeah, that's fine, except it's not right, right? This is just not what you do. You can't distribute a power over a sum. If you really want to take a plus b and you square it, so wait a minute, let me really emphasize this. That's not equal, but that's the line that goes there. Because actually a plus b squared is what you get if you multiply a plus b times a plus b. And that requires the FOIL rule. And you get first times first gives you a squared, then outer times outer and inner times inner are both a times b, so you get twice ab, and last times last gets you b squared. So don't fall for this foolery. You know, don't try to square a sum of two things and just say you can square the pieces, because you're forgetting about the outer times outer and inner times inner terms from the FOIL rule. Okay, when I give you a function like I did in the examples before, like f of x is equal to some formula, and I want to be a little bit generic here, so I'm just writing the words a formula. If f of x is equal to some formula, you have an important job to do, which is to figure out what are the allowed inputs. In other words, what is the domain? And that's a bigger deal than you might think. Because a lot of times I'll give you a formula, and it's a formula for something that's in a particular setting, you know? And in that setting, for instance, it might only make sense if you were dealing with positive numbers. So in that case, I want the domain to be positive numbers. That needs to actually be specified up front if you really want the domain to be, you know, some particular set of numbers that's determined ahead of time. If such a thing is not done, there's a default thing we do, and it's called the default domain. So let's say this. You can specify a domain, or you can accept the default domain. Let me provide a couple of examples, one of each of those. Suppose I want to specify the domain, so I say f of x is equal to, I'm getting tired of using the same example over and over, so I'm going to switch and have 2x plus 3 be the function. If I want to also specify the domain, that's done by putting a semicolon and then doing some math that specifies what inputs you want to have. Like maybe x is bigger than 0. That's specifying a domain. Now, I bet you have seen this kind of thing before, and it was utterly invisible to you because you didn't know what the heck they were doing. Why? You probably thought, oh, there must be like a typo. There's some weird equation left over on the end there. It was not a typo. They were actually trying to tell you something. Half the time you don't need to worry about that, but when they're specifying a domain, it'll always be seen this way. You've got a semicolon and then some inequalities or maybe interval notation to be used there. So that's a specified domain. Watch for that from now on. If you see semicolons and inequalities appearing just to the right of your function definitions, that's what it's about. The default domain is a different thing. And in this case, if I use the same function, but I didn't say anything after that, then you get a different domain, because the default rule is this. You look at the formula and you ask yourself, does it ever break? Is there any x values that would make that be, you know, not work out, not be a thing that could be computed? We talk about a function being defined, and I think they were careful in your algebra classes to say that some functions are not defined for certain x values. Essentially, the only thing that we can go south with at this point in your careers is dividing by 0 or taking square roots of numbers that are negative. And this particular function has no division in it, so we're good on dividing by 0, and it has no square roots or fourth roots or sixth roots. You can't have any even roots. Oh, it's not that you can't have any, but if you have some, you produce the possibility of taking a square root of a negative or an even root of a negative, which is undefined. All right, so 2x plus 3 without a specified domain after it, it's a free-for-all. Any x value will be fine. You can stick any x coordinate into that and you come up with a y. So here, the default domain is the entire real line. Minus infinity to infinity. I feel like I want to put a colon in there or something. These two things, while they have the same function in them, they look very different. I'll give you an idea what the graphs look like. 2x plus 3 hits the y-axis at 3 units, and it has a slope of 2. Probably should use colors. But if I have 2x plus 3, but the x coordinates are only positive, what I get is this graph. From x equals, it doesn't include x equals 0, so 0, 3 is not on the graph. But anything to the right, that's an x value that's in the domain of this, and we calculate a y value, and we get all these points on the green line. On the other hand, if I don't specify the domain, maybe I should just make a new axis. I was about to draw it right on top of that one, but that's going to be hard to see. If I don't specify the domain and I accept the default, then that point, oh no, my blue is invisible blue. Oops. That point's on there. Oh, another invisible blue. Yeah. I gotta dig into my marker supply here. Here's red, this one should be good. So in the one case we get a ray, in the other case we get an infinite line that goes both directions. So any x value, you can get a y here. Only positive x values have a y. It's admittedly not a huge difference, but it's a different thing. So part of the identity of a function is what's its domain. If it's specified, that's one thing. I mean, you just have to take whatever is specified. But if it's not specified, we have to use the default domain rule, figure out what might go wrong with it, and eliminate it. So I want to give you a little. In the worksheet, there'll be a little more practice with finding default domains. But in the textbook, there's in the midst of the text example. It's example 1.4.3. It has, in this example 1.4.3, it has like 6 different formulas for functions, and you're supposed to just figure out the default domain in each of them. So the first one, it's g of x, and it's equal to the square root of 4 minus 3x. This doesn't have any division, so we're not going to get in trouble with that, but it does have a square root. So if 4 minus 3x is negative, this will be broken. So what we have to do to figure out the domain of this thing is we need to solve for when is 4 minus 3x not negative. In other words, when is 4 minus 3x greater than or equal to 0? That can't be that hard. Let's see, subtract 4 from both sides. You get negative 3x would be greater than or equal to negative 4. A little quick test on your algebra skills. I got a minus sign on both sides. Can't I just cancel those? Well, not when you have inequalities. There's a little funny business that goes on with inequalities. And it's that if you multiply by a negative on both sides of an inequality, that's valid to do, but the sense of the inequality flips around. So if you need to do this, get rid of the negative signs, you end up 3x and 4, and the inequality now goes that way. And then finally, divide by 3. That's an okay operation. We're actually think of it as multiplying by 1/3. A positive number doesn't change the sense of the inequality. So x less than or equal to 1/3. All right, so that means the square root of 4 minus 3x only exists when x is smaller than or equal to 1/3. That is, if I plotted a number line here, 1/3 is about there. This is where the domain is. So what I'm drawing there is kind of the shadow of the graph. It turns out because it's a square root, the graph looks something like this. It's like a parabola stuck on its side. I love to do this kind of thing in Desmos, because it's kind of good that way. If you put in square root of 4 minus 3x, it'll just draw this thing perfectly, and you can see where the domain is. Anyway, that's one of the elements of this example. I don't want to do them all, but I thought it might be good to do one or two other ones. Maybe just two other ones. So let's also look at number 2 in this example 1.4.3. The name of the function is different, and the formula for the function is different. It's a fifth root of 4 minus 3x. And I'm sorry, what was the function? H, I think is what they call it. H of x equals that. Now what's the default domain? Well, there's no division, so we don't have to worry about dividing by 0. But there is a fifth root though. So do I have to worry about this number underneath the radical being negative? No, because that concern about negatives under the radical is only it's really only an issue if the radical is an even power. So if it's square root or fourth root, you've got to worry about that. With fifth root, it's fine. You can take a fifth root of a negative number. If you don't believe me, let's see. The fifth root of negative 32. I'm going to stick it in a calculator. I'll tell you it's negative 2. And the reason I know it's negative 2 is actually because if I take negative 2 and I raise it to the fifth power, well, there's 5 minus signs in that, so I'm going to get a negative number. And 2 to the fifth, I don't know if people are handy at this, but I've developed a facility of doubling while counting on my fingers. So 2, 4, 8, 16, 32. Negative 32. So because negative 2 raised to the fifth power gives me negative 32, that means I'm turning the tables on the fifth root of negative 32 must be minus 2. So that was just an example. You can take fifth roots of positive or negative numbers. It's not an issue. So, okay, this was all sort of just to convince you that I could take fifth roots of negative numbers. What does that say about domains? It says you can't go wrong. There is nothing that's going to break that function. That is, there's no x values that it can't compute the y value that goes with them. So your domain under the default rule is all real numbers from minus infinity all the way up to plus infinity. Okay, last one I want to do is the last one in the group. It's number 6. I think they ended up with like having to go to fairly unusual function names. Yeah, I of x, capital I of x. And the formula in this case is 3x squared over x. Now, I don't have any square roots or fourth roots or sixth roots or whatever, but I do have division. And if I was concerned about dividing by 0, that would mean this x here in the bottom would have to be 0. And what does this thing look like if you plug in 0? I of 0 would be 3 times 0 squared over 0. Well, that's a 0 up top and it's a 0 downstairs. It's 0 over 0. What do you do with that? That's undefined. But there's something odd about this, which is I feel like I should be able to cancel this x in the bottom with the x in the top, or with one of the x's that's in the top. I mean, that I of x is also, think of it this way, it's 3 times x over x, and shouldn't we be able to just knock out 2 of those and you end up with 3x? Well, yes, and also no. So the problem is that this is not wrong. When you stick 0 in for I, you get 0 over 0. So that's an undefined expression. When I stick any number besides 0 into this thing, I'm going to get the same thing as 3 times that number. But when I stick 0 itself in, I get 0 over 0. And this again has to do with this, this concept I mentioned last class about limits. As you approach x equals 0, the output approaches 0. But when you actually get there, it's undefined. It's a little bit of an oddness. The graph of I of x, I'll show it to you. It has a hole right there, and other than that, it's a straight line with slope 3. That's what the graph of I of x looks like. The graph of this thing that I did when I simplified it doesn't look like that. It's just a line of slope 3 that goes right through the origin. These are not very different, but that one's got a point plucked out of it, and this one has that point still in there. So these things are not exactly identical. You only say things are equal if they're literally identical all the time, and this isn't quite the case. So the object lesson here is don't do any cancelings like that. Keep the thing in its sort of the way it's handed to you form to check for when it's undefined. I'll make it, I feel like I'm beating a dead horse here, but there's a quick way to see that this is not quite the same. What's really going on when I cancel something like that in the numerator and denominator? What I'm really doing is dividing by that number. So by turning it into calling it canceling, I've just kind of hidden from you the fact that I was actually dividing both numerator and denominator by x. Well, dividing numerator and denominator by x is perfectly fine unless x happens to be 0, in which case that's just a legal operation. So that's why we get slightly different output when x is 0 than in this thing than we do in that one. Here we get undefined, here we get 0. Okay, so this section ends with a brief little bit about modeling using function notation. The main thing, and this is a bit of function notation that I think people find tricky. It's what's known as a piecewise definition for a function. I want to say something first about piecewise functions. There's actually many times when you use piecewise definitions, when there are actual things you care about computing that are done in a piecewise way. For instance, income taxes is a piecewise function. When you compute your income tax, there's a breakpoint where up to, I think it's $104,000 a year, use the tax tables, and after that you have to just multiply by some percentage. The tax tables themselves have piecewise breaks in them, but that's maybe not the best example. I'm not sure everybody's had that experience of dealing with the tax tables. Here's another one that I've seen sometimes, although these days almost everybody uses the unlimited data plan, but in the early days of smartphones, they would say, okay, you can have a gigabyte a month for this much money, and then anything you spend beyond that is, you'll be charged on per megabyte basis. Or you can do the unlimited plan, which is just the set fee, right? Well, that's a question about, how much data are you going to use? If you stay below your 5 gigabyte cap and you never get into the part where they're charging you a little extra on the megabyte per megabyte basis, then it's fine. But that's a piecewise definition. You've got a cost. If you think about your data usage as the x-axis, you got a fixed cost until you get to that 5 gigabytes, and then it starts climbing after that because you're being charged per per megabyte, I think it is on the plan after that. So here, it's just a constant number. Here, it's some kind of line equation that you have to deal with. Okay, so how do we denote that sort of thing in reality? I'm going to give you the one out of the example we're about to do, which just closed it up. Here it is. Okay. So I'm going to give you a function that's the height of a little toy rocket as a function of time. And there's two different places where we have two different formulas. So what we do to denote that is to write a sort of a giant curly brace, the same curly braces for sets, but big size. And there's two options. One is 0, and the other is a slightly complicated formula involving t. It's 100 minus 5t squared. All right, so these are the two different rules that you use for computing. The one that's more difficult is only used in a certain interval. It's used when t is between 0 and 20. And this other guy here is used if t is greater than 20. Whoops, I guess I got to go strictly greater than 20. I'm sorry, I knew something was wrong with that. I left out a letter. That was supposed to be 100t minus 5t squared. That's better. So the reason that I knew something was up is this particular h of t has been designed so that it matches when you're at 20. If you stick 20 in here, you get 2,000 minus 5 times 4, 20 times 100, yeah, 2,000 minus 5 times 400, yeah, 400, yeah. Okay, 2,000 minus 2,000, yeah, that's 0. And so at t equals 20, this formula gives you the 0 value too. That is, these things match. If I was to make a graph of that, it looks like this. That thing right there turns out to be an upside down parabola, just like that. And you hit 20 right there. It's the x value. This is 0. 0 to 20, we're on that parabolic arch. And then afterwards, we're on 0. So it's confusing. I've got the graph is at 0, and also the x-axis is, or the t-axis is at 0. We normally call the axes x and y, but in this case I would call them t and h, because t for time and h for height. So what this is saying is you launch the rocket, and over the first 20 seconds it goes up in the air and comes back down. Now it's slammed into the ground, and it stays there afterwards. There's probably a reasonable way of extending that into the past. For negative t values, you'd also have 0, but we usually don't spend much attention on that negative part of the graph. Think of the flight starting at t equals 0 and heading on from there. Okay, there is a little practical problem that's given in here, which is, well, actually there's a two-phase problem that's given in. This is the setup. The first problem is evaluate h of 10 and also h of 60. So h of 10, which of the two formulas are we going to be using? The complicated thing or the 0? The complicated thing, because the 10 is in between 0 and 20. All right, so what is h of 10 going to be? It's 100 times 10 minus 5 times 10 squared. That's 500, that's 1,000. Okay, this is 500. That wasn't so bad. What about h of 60? that's not between 0 and 20, it's greater than 20. We use that one. Okay, so h of 60 is very easy. You just write in 0. So that's the first problem they have. I guess I don't need the graph, so I'll give you the last problem. And this is it for us today. The last problem is to solve the inverse problem here. Find h of t when is the height equal to 375? So that's basically, you know, these two things are sort of the two types of questions you can be asked. Stick in something for the dependent variable. Whoops, I just said it wrong. Independent variable, the input, and get an output, or choose something for the output and see if you can figure out what input creates that. Now, for us here, this is a little bit tougher. But I definitely know we're not going to be using this formula, don't I? Because h of t is definitely not 0. So if there's going to be an answer at all, it has to be in here. And that means we're interested in this when t is between 0 and 20. We're expecting t to be between 0 and 20. So I know I'm going to use that formula, equal it into this number. Can I do this? Sure, I can. I think, though, what I want to do is, and this is sort of the standard procedure, by the way, push everything to one side or the other of the equation. I kind of don't like the minus sign on my t squared, so I'm going to move things to the right. That is, I'll add 5t squared to both sides, and then I'll subtract 100t. I'll end up with 5t squared minus 100t plus 375. Now, I was just thinking about that in terms of moving everything to the right, but that means there'll be nothing left on the left, which is 0, and I just prefer to write that on the right-hand side rather than the left-hand side. So, oops, I left off the square root. 5t squared minus 100t plus 375 equals 0. Why did I do that? Well, that's a quadratic formula, and there's a way to easily solve it. One thing that's kind of cool on this particular quadratic formula, do you notice that every one of these ends in either a 5 or a 0? That every number in there is divisible by 5. So I can divide through by 5. I can do that on both sides, but that doesn't have much of an effect on the right-hand side, because 0 divided by 5 remains 0. So it's the same thing to say t squared minus 20t plus, probably want a calculator for that, don't I? 375 divided by 5. $75. Oh, I should have done that in my head. Okay, so can we solve that now? It turns out, yes, you can go via two routes. You can either go by factoring or the quadratic formula. I'm going to try factoring. I just want to see if I can think of this as coming out of the FOIL rule somehow. Now, so I put a t and a t because first times first got us that t squared, right? But I now need to put numbers here and here so that their product gives us this for last times last, and their sum gives us this minus 20. Now, if two numbers are going to have a product that's positive and their sum is negative, they're both going to need to be negative. So you figure that much. Now I'm looking for two numbers whose product is 75 and that add up to 20. And oh, there they are, 5 and 15. All right, so that's not so bad. You've got a product of two things equals 0. This one's either 0 or this one's equal to 0. And that means t is equal to 5 if that one's 0, or t is equal to 15 if that one's 0. And that actually makes good sense if you think about it on the graph we had here before. Remember the graph that looked like this and then stayed at 0? 375 is about at that height. And what we just realized is there's a place at 5 seconds where we cross over h equals 375. And then there's another spot right here at 15 seconds where we pass through that same altitude but going down. So on the way up, we pass through that height, we peak out somewhere above that, and then we hit that height again on the way down. Fun. Okay, so that's it for section 1.4, and we'll see you on Wednesday.